Okay, here we go. Here we go. Here we go. Okay, welcome back. I hope we had a great spring break. Happy Monday. Today we are going to cover another physics topic called work. Last class we talked about density. We will use some of the density stuff we did last class in today's class. Project 5 is officially due at this moment. Throw it into the green folder if you have it. If you don't have it, I'll take it late, but there are lateness penalties. So throw it in the folder if you have it now. Project 6 is officially assigned, although I handed that out the class before break, just in case people wanted to look at it early. I also lied to you when I handed it out, and I said you have all the tools you need to do Project 6. There are essentially 3 problems on Project 6, and you could do one of them with the current tools. We're going to talk about the second problem today, and the third problem is next class. So I think I was a bit premature handing that thing out, but maybe some folks had a chance to look at it. So I think that's about it. This project 6 is due April 4, which I think is Monday coming up. So 1 week from today is when our next project is due. Any questions on the calendar? Okay, and up on the screen here, you can see test number 2 is not too far off. It's coming up on Wednesday, April 6th. So a week from this coming Wednesday is our second test, and it is not too early to start studying for that test. The test covers everything since the first test. So lessons 13 to 24, 23? 23. Yeah, a week from this Wednesday. Yeah. Chris? So all the practice problems I have are in that big packet that I gave out on the first day of the semester. Right, so you'll just make sure you use the relevant ones for this test. Other questions? Yeah, how about that for killing a spring break buzz? All right, starting on the top of page 62. Here we go. Daily summary. Work is another concept from physics that we can calculate using our slicing technique, which again leads to an integral. Number 0 is a reminder that part of the homework was to read this article, a great article by Steven Strogatz. It slices, it dices. It is printed there. There's also a URL if you feel like going to look at it online. I know that not all of us are officially doing homework, but regardless, I think it's a worthwhile read. So just reminding folks that it is there. Number 1, some preliminary facts. So first of all, Ted tells us that work is equal to force times distance. This is a formula we've seen in our physics class. Yes? Okay, and sometimes force is just given to you, but oftentimes force gets replaced by weight if it's a force due to gravity, right? And so our formula for weight is down below. Weight is mass times acceleration. Yeah? Okay. And so let's think about work for just a second. There's a misconception about work that if you do something that makes you tired, then you are doing work. And that is not necessarily correct. I could push against this wall all day long and get really tired. Am I doing any work? Not according to the physics definition, because the physics definition of work involves distance. And I'm not going to move that wall at all. And so my distance would be 0, and so my work would be 0. Okay? Something has to move in order for work to take place. So here's a common work example. I can take this eraser and I can raise it 2 feet. I didn't get very tired, but I did do some work here because there was a force I had to apply because gravity was trying to resist this motion, right? And so there was a force I applied upwards by about 2 feet. Multiply the force times the distance. That tells me how much work I did. Okay? Hello? Yeah, go ahead. There are some units in this table. We'll come back and look at them as we need to while we do these problems, but just one thing here. The unit for mass almost everywhere in the world is kilogram. Here we use the slug. If that's not a reason to switch away from our system and into metric, I don't know what else is. Seriously, slug is one of our units. Okay, so let's give this a shot. We're going to jump to number 3, and I'm going to change this 1 kilogram to 2. Everybody just make that real quick change. So how much work is done lifting 2 kilograms of iron 3 meters off the floor? So picking it up from the floor, lifting it 3 meters up, and we want to know how much work we did, so let's give it a shot. We know that work is equal to force times distance. Is 2 kilograms the force of that iron? No, 2 kilograms is the mass of the iron. And so we do really need to know our stuff here and change that word force into weight times distance. And we have already seen that weight is mass times acceleration. And so unpacking this guy gives me a very common alternate formula for work, It's mass times acceleration times distance. So anytime I'm given a mass, I'm using this version for work. But if I happen to be given the force directly, I'm using F times D. Okay, so what's the mass in this example? It's now 2. I changed it. Make sure you make that change. Times acceleration is 9.8. The distance in this case, 3 meters. So we crunch the numbers. What is it? 58.8. 58.8. Good. Let's get some units here. The units for work in almost everywhere in the world is the joule. So 58.8 joules. Okay, so no calculus there. So how does calculus come into play? Let's take a look at number 4. So there's a 45-meter rope with a mass of 30 kilograms. That's the mass of the entire rope, is 30 kilograms, is dangling over the edge of a cliff. Ignoring friction, how much work is needed to pull the rope up to the top of the cliff, right? So you're standing there at the top of the cliff. You're going to pull this rope up towards you. So standard wrong way to do this is this force times distance business. Well, that's okay. And then mass times acceleration times distance. We're still okay here. What's the mass of the entire rope? 30 kilograms. Acceleration is still 9.8. Distance the entire rope is going is 45. So you can crunch those numbers together. It's already been done. It turns out to be this 13,230. So what's wrong with that? It gets easier, right? As you pull that rope up, there's less weight resisting you're pulling upwards, right? And so in fact, every time you pull, it's easier than the previous time you pulled. And every time you pull a millimeter, it's easier than the previous millimeter, right? And so what we need to do is say, okay, we're going to pull this thing just a millimeter at a time, and then we're going to recalculate the weight of what's left over hanging down, right? And then even a millimeter is an exaggeration, right? We're imagining doing like infinitely thin things with infinitely many little tiny pulls up, and that's where the integral is going to come in. So we're going to slice this rope. We're just going to pull a tiny bit up at a time. So let's try it here. So here is my cliff. Up here, I've got a little pulley. All right, now this is not a pulley problem, but this is just my way of highlighting that there's no friction. We're not pulling against anything on the corner of that cliff. And so what we're going to do is say, hey, let's just call x some distance here. Let's suppose that x is the distance from where the bottom of the rope is to the bottom of the mountain or whatever it is, dangling over the cliff. So how far it has already traveled can be x, which means how far it has left to travel is what, 45 minus x? Everybody buy that? So we've pulled it up x already. So 45 minus x is what's left. And we're going to imagine pulling this rope just a tiny bit. And so we'll call delta x just this tiny little millimeter pull upwards at this one moment in time, right? This is like a video, and we just kind of pause the video and pull it a tiny, tiny bit, hardly any change in the video. Okay, so let's see if we can figure out the work done for pulling our slice. Okay, so force times distance still unpacks to mass times acceleration times distance. Let's do the pieces here. Mass is the trickiest part. I'm going to leave that blank for a second. Acceleration is still 9.8. The distance I am pulling is something I symbolized. What is it? The distance I'm pulling is what I'm calling delta x. I'm imagining just a little millimeter pull, okay? We're calling that small change delta x. Okay, so the mass is where the complication is. We're trying to figure out how much the mass of the leftover rope is at any particular moment. Okay, so let's see. I know that I have 30 kilograms spread out over 45 meters. So 30 kilograms over 45 meters. What's a good name for that fraction? It is 2/3. What? It is a ratio. My question is perhaps ill-defined. 2/3 of a kilogram per meter. I'm changing. That's a density, yeah? It's 2/3 of a kilogram per meter. Super. So then the mass of the rope that's left to pull, well, it's 2/3 of a kilogram per meter times how many meters? Is the 45 minus x. So 2/3 times 45 minus x. And it's going to be pretty common for us today to use that idea of density. So in this case, it was a density times a distance or length. All right, so that thing right there represents how much work you have to do to pull that one little tiny slice. I'm not really imagining slicing the rope up. You could do it that way, but that's not how I'm doing it. I'm imagining a slice where I just pull a tiny bit, the entirety of the rope that's still dangling. Okay, and so if I wanted to do the work of all of these little tiny slice pulls, I just do a summation of things that look just like that. And then the actual work, that summation turns into an integral. And so we're going to integrate exactly that thing. 2/3, 45 minus x, 9.8, delta x becomes dx. Zero to 45, everybody buy it? So, if you do 45 to 0, I think you're going to get a negative number. The x when we start this process is how much? Yeah, it's x is the gap. Yeah, totally fine to call x what is still hanging, in which case I think things would change just a little bit. You might do 45 to 0, still get the same positive number. Okay, so typing that in, or that's easy enough to do the integral by hand. So I think I've got a number written down. We'll just write it instead of waiting. I don't have a number. Do I have a number? No, I don't have a number. So it is what it is. It's not interesting. The thing that I want to highlight here is this delta x becoming a dx. Now I know we've talked about that before, and magically there's always been a delta x that converted to a dx in all of these translations that we've done. But I just want to highlight this project that I handed out last time, but is officially assigned now. The project that is she works hard for the money. You got to make sure that your initial expression has a delta x in it. There might be temptations to have something that looks like a delta x squared. Like if you get a delta x squared in your original like sigma notation, that's a real problem because you cannot translate that into a dx. It could be that your delta x squared is a perfectly legitimate way to start the problem, but it doesn't go to the integral. And so you need to come up with a way to write your initial expression so it has a single delta x. It's not just a symbolic thing. It needs to be there for us to translate to an integral. All right? Okay, so that is that problem. Let's move on to the next page. Oh, one small thing. What could we do here? This 294, and that's N for Newton. That's the weight of the entire rope. That's just multiplying the 30 times 9.8. So the whole thing weighs 294 newtons. There's a shortcut to doing this problem that completely avoids all of the calculus. You could take this 45 kilogram rope and maybe compress it to like a single dot of rope that contains all of the weight of this rope. It weighs 294 newtons, right? And where would you put that compressed point of a rope? Right in the center. And so how far does that little dot of rope have to go? 22.5. And so you could just do force times distance, 294 times 22.5. You'll get the right answer, the same thing that this integral will get. Please do not do that. It's a clever workaround, and it's fine. It's going to be fine in some of the problems that you do, but I'm looking for a calculus thing here, okay? We could also change the problem just a tiny bit and make it so you can't do that workaround. Instead of having this rope be uniform density, I could have the density change. Maybe the density is x squared kilograms, depending on where you are, right? So it's easy to tweak it so that it's not possible to just do that shortcut, but even if I give you one where it is, don't. I'm looking for calculus. Okay, number 5, we're skipping. Let's jump to 6. A water tank in the shape of a right circular cone of height 1 meter and top radius of 0.5 meters has a column of water that has a height of 0.5 meters. Find the work that must be done to empty the tank by pumping the water over the top edge, and then there's something in there about the density of water. So we're going to take all this water and we're going to pull it all the way up to the top of this tank. Fair? And there's going to be work done. Now this one is more complicated. So what we're going to do is slice the water up in such a way that the molecules of water that we grab all have to go the same distance, because we know work is force times distance. And I'm not going to be able to compare the work done for that water molecule with the work done for that water molecule, because the one at the top requires a lot less work to move. Yeah? So we're slicing up the water here. How are we going to slice it? Horizontally. So we're going to have these little horizontal things of water here. Something like that. And if you imagine that being thinner than I've drawn it, then all the particles of water in that slice move essentially the same distance to get to the top of the cone. Okay, so how about we do the same thing we did before. Let's call the little thickness of that guy delta x. And let's say that x is the distance that that thing is to the bottom of the cone. And the reason that this is more complicated than the rope is that the rope was essentially, it was just a uniform cylinder, right? And so like you just sliced it horizontally and it's just the same density every place. This true water has a constant density, but there's more and more water. There's more and more volume as you move up this column of water, right? And so the amount of force required to lift that slice is not the same as the amount of force required to lift a slice that's higher, because there's just more water higher, yeah? So this one's more complicated, but let's see if we can start with our basic work formula. So we're doing work for one slice. So we'll start with our force times distance.
Yeah, I'm wondering what we're actually doing here. Like, are you pumping it into the bottom?
Okay, so what we are doing here is going to be physically hard to do, but calculus-wise will make it easier for us to do. I think typically what you do is you put like a big straw in there. I don't know what they're called, but like an actual big, like a massive tube that would suck all this water up, and it's probably going to suck up, you know, like you might just stick the tube all the way in and then pull the water all the way up to the top, right? But if you're trying to do this in the most efficient way, what's the first water you would grab? The water at the top. Because as soon as you start grabbing water at the bottom, the water at the top falls down and all of a sudden has farther to go, right? And so what I'm going to imagine doing is taking my like massive straw, grabbing this entire like a little millimeter thick slab of water up there. So this is like a really wide straw. Just suck that all up right to the top and then it's gone. And then I move my straw down a little bit. This is a magical straw where it can get a little bit smaller, and then I'm going to grab the next circle of water. So you're taking the water in slabs, kind of independent of gravity pulling the other water down to fill the space. Chris? So it's going to turn out to be the same answer as putting the straw all the way to the bottom? Oh. You bet.
Pushes the water at the bottom down up through.
Yeah, I buy that. I buy that there's some kind of forces and pressures here, but I don't understand them. So I'm but
when you put a straw in a cup of water,
yeah.
Water in the straw is the same as water.
Right. All right. So math, if nothing else, math is a democracy, and it seems like there's a majority here. So we'll say yes, it's going to be the same answer. But awesome. Okay, we're going to unpack this. The force becomes mass times acceleration, right? So we've got our mass times acceleration times distance. So far, so good. The mass is a formula that we saw on a previous class. We're given a density there. That 1,000 kilograms per cubic meter is a density. So the formula for mass that we saw before was the volume times the density. I'll highlight that is that. Wait, remember that formula? This is the 3D version of our mass formula. And then finally, the volume of that slice, well, that little slice is a tiny cylinder, right? So what's the formula for the volume of a cylinder? Pi r squared times height. And then copying everything else, delta A and D. So that is the same as that. So at this point, it's not going to be too hard to just start replacing all these guys with the right things. There's a little bit of work to do. But I really like the unpacking that happens. That simple force times distance all of a sudden became, you know, like 6 different things multiplied together. Yeah, delta for density. Thanks. Baby delta. Okay, let's give it a shot. Pi times the radius. Is the radius of my slice constant? No, all right, let's come back to that. I'm just going to leave it blank for right now. So it's going to get squared, whatever it is. The height, careful about the height. It's not necessarily the height that you are from the bottom of the cone. This is the height of that cylinder. What is it? That's delta x. Times delta is the density of water, which is given as 1,000 kilograms per cubic meter. I'm not going to write the units, but just want to point out that everything's going to work out here. When you do this pi r squared h, what are the units? Is cubic meters, right? That's the volume. And so that's a cubic meter thing times the 1,000 kilograms per cubic meter. And lo and behold, we just have kilograms, which is exactly what we were after here for the mass. Volume times density gives me kilograms for the mass. Okay, so that's that guy. A is still 9.8. Okay, D. We have a tiny bit of work here. D stands for the distance that this water is traveling, that particular slice is traveling. How far is it traveling? 1 minus x is good, right? Because we called x that how far it was from the bottom. And so 1 minus x will get me to the top. 1 minus x. Everybody okay with that 1 minus x? Good. You like that? All right, the radius. Okay, so the radius is the last part, and it changes. So we need to figure out a formula for the radius. What's the only letter that's allowed to be in the parentheses here? It's got to be x, right? Delta x needs to be x. Okay, so we need the radius in terms of x. Right now it's not labeled at all, but I think we've got a little geometry result we need to do here. If I take that cone and I just slice it right through the center, all the way to the bottom, I'm going to draw what I have left. So there's the triangle for slicing the cone straight through the center. There's a little triangle where my blue slice is. We already decided that it's a 0.5 up here at the top is the radius, and then a 1 is the whole thing. And x is what we called this guy. And what we're after is the radius of that little slice of water. Yeah? We remember similar triangle thing we did. We've done this a couple of times in previous classes. So what to what? Let's see, we can do r is to 0.5 as half of the cone. I'm slicing the cone to make triangles. The top of the triangle. I'm imagining doing the whole cone. Oh, gotcha. You're right. That's what I'm imagining. I'm imagining the triangles over on that side. 0.5 is the one and r is the other. You're right. And then, okay, so that is to 0.5 as what is to what in the small triangle first? X is to 1. Okay, great. What letter am I solving for here? Trying to solve for r so I can put x's in the parentheses. Okay, so we solve this for r. And we get r is 0.5x. which is a simple enough relationship. You might have been able to just grab it from the original picture without doing all the similar triangle stuff, right? The radius of 0.5 is half of the height. That's going to be true for every slab of water that we pick. The radius will be half of the height. Okay, so 0.5x goes in the parentheses here. And I think we're good. And so we'll just write one last thing here. Total work is equal to, again, summing up all of these little work slices leads to an integral. So all of this stuff is copied basically pi 0.5x squared. Delta x becomes dx, that's important, times 1,000 times 9.8 times 1 minus x. And the limits, 0 to 1, 0 to 0.5. It's the only place the fact that the column of water is half a meter comes in. So 0 to 0.5. We're only doing this where the water lives. Okay, and again, we're not going to spend our time typing it in, although you could do that integral by hand. It's around 200.44, and then again, joules is our unit for work. Okay, so when you're ready, you're starting the activity right there. I will walk around to help. Draw very careful pictures and label them well.